Welcome to the Deep Dive. This is where we take a whole stack of sources, articles, notes, research on a complex topic, and, well, we boil it all down for you.
Yep, we give you the essentials, the surprising bits, the stuff you really need to know without you having to wade through everything yourself.
Think of it as your shortcut to really getting up to speed.
And today, we're tackling something pretty critical. You, our listener, pointed us towards the headaches of managing modern software and how observability is becoming key.
Exactly. We've got a great mix of materials you sent over, stuff on OpenTelemetry, microservices, observability engineering principles, practical guides, even specifics on .NET performance.
A really good selection.
Yeah. So our mission today is pretty clear. Let's
Right.
figure out why it's so hard to understand what's going on inside our software these days.
And then how new tools and ways of thinking are helping us, get a grip on it all.
We want to arm you with some practical insights, whether you're deep in the code yourself or just curious about how these complex systems tick. Okay, let's dive in. First up, what makes watching modern software so difficult?
I mean, the sources all point to one main thing: complexity. Just sheer runaway complexity.
Right.
Especially with the move to the cloud and things like Kubernetes, systems are just so dynamic now.
Dynamic how? Like, what does that mean in practice?
Well, imagine you've got a slow API call, or maybe users are saying file uploads are failing, trying to trace that problem when it involves multiple independent services.
Huh.
It's tough.
Uh-huh.
One source really highlighted the pain of jumping between 5 different monitoring tools just to piece together what happened for one request.
It sounds exhausting, like detective work with clues scattered everywhere.
Exactly. And then you add Kubernetes, so you have these containers, right? Little packages of software.
Yep.
They can be created and destroyed super fast. So if a container crashes, any logs inside it, poof, gone.
Oh, wow. So the evidence literally disappears.
Pretty much. The ephemeral nature, as they call it, makes post-mortem analysis really hard sometimes.
And I guess old school debugging, like stepping through code on one server, doesn't really work anymore either.
Not nearly as well. In the cloud, the actual server, the node your code is running on, might change any minute.
Ah,
So trying to pin down, say, a slow node or some weird configuration issue, it's like trying to hit a moving target in the dark. The whole execution environment is just constantly shifting.
okay. So the ground is constantly moving beneath our feet, basically.
Yeah.
And that makes the traditional ways of keeping tabs, what we used to just call monitoring, makes them less effective.
Yeah, definitely. Traditional monitoring, as one of the sources explains, mostly looks for known problems, failures you've seen before.
So you set up alerts like, if CPU hits 90%, tell me. That kind of thing.
Exactly. Predefined thresholds for predictable issues, which is fine. I mean, it's useful. But what happens when something completely new and unexpected goes wrong?
Which happens more often now with all this complexity.
That's the point. These distributed systems can fare in ways you just couldn't predict. The source on observability engineering mentions that developers used to rarely hit truly novel logic errors, but the interconnectedness now makes it much more common.
Okay, so monitoring knowns isn't enough. What about dashboards? We all love dashboards, right?
Well, yes and no. That same source questions how universally useful they are. A dashboard that's perfect for your application might be totally confusing for someone looking at a different system.
Right, different tech stack, different architecture.
Exactly. You need deep application-specific knowledge to make sense of it. It's an abstraction, and sometimes you need the raw details, especially for those novel problems.
And metrics themselves, they give you the big picture, but maybe miss the details.
They can, yeah. An average response time might look okay, but it could hide the fact that, 5% of your users are having a terrible experience. Metrics aggregate things.
And logs. Loads of logs.
Logs are great, humans can read them, but machines. Parsing terabytes of unstructured text to find that one error message. At scale, it's a massive challenge.
Okay, complexity, dynamic environments, limits of old monitoring. It's a tricky situation. So what about the tools we do have, the telemetry platforms?
Yeah.
Are they solving this?
They help, but the sources point out some big drawbacks too. Cost is a major one.
Oh, yes.
Some of these proprietary managed platforms are, let's just say, very expensive. And then there's vendor lock-in.
Meaning once you're in, it's hard to switch.
Extremely hard. You integrate deeply, build dashboards, train people. Moving becomes a massive project. So you're kind of stuck with their features, their pricing, even if something better comes along.
Like golden handcuffs.
Pretty much. And often no single platform does everything you need, right? So you end up juggling multiple tools anyway, one for logs, one for metrics, maybe another for traces.
Which sounds like its own kind of nightmare to manage.
It can be. And the alternative, trying to build your own observability platform from scratch.
Sounds ambitious.
Hugely ambitious and expensive. You're basically building a complex distributed system just to monitor your other complex distributed systems. It takes immense engineering effort away from your actual product.
Okay, so it's either potentially costly vendor lock-in or a massive internal build. Not ideal. And all this data collection,
Yeah.
it must use up resources, right? CPU, memory?
Oh, absolutely. Collecting, processing, storing telemetry data, it all consumes resources on your servers, on your network.
So the act of observing affects the thing you're observing.
To some degree, yes. There's always an overhead. You need to be smart about it. One source warns against monitoring what doesn't matter. Just collecting data for the sake of it can be wasteful and costly.
Right, you need to balance the value you get from the data against the cost of getting it. Makes sense.
And figuring out which data is valuable is key. Is a metric useful on its own, or only when you correlate it with, say, a trace or a log event?
Yeah. Context matters.
Yeah, it really does. And then you have things like high cardinality metrics. Think like metrics that include user IDs or request IDs.
Super useful for drilling down, I bet.
Incredibly useful, but also potentially very expensive to store and query because there are so many unique values. So organizations need strategies, sampling, aggregation, maybe dropping less critical data to manage those costs.
Okay, wow. So complex systems, old tools struggling, vendor issues, resource costs. It feels like we are painting ourselves into a corner, but obviously something changed. The whole idea of observability emerged. What is that, fundamentally?
Yeah, it's a key shift. Observability, as the Observability Engineering book puts it, isn't just monitoring, it's a property of a system.
A property.
Meaning it's a measure of how well you can understand the internal state of the system just by looking at the data it outputs its telemetry. Crucially, it's about being able to ask new questions.
New questions. Unlike monitoring, which answers predefined questions.
Exactly. Monitoring checks for known unknowns. Observability lets you explore unknown unknowns. When something novel happens, you have the data and tools to dig in and figure it out, even if you never predicted that specific failure mode.
Okay, that sounds much more powerful. More like being a detective than just a security guard watching monitors.
That's a good analogy. And a huge enabler for this is OpenTelemetry.
Right, OpenTelemetry. We hear that name a lot. What's its main goal?
Its core mission really is to standardize how we generate, collect, and export telemetry traces, metrics, logs. To address all that fragmentation and complexity we talked about,
Standardize how?
two key concepts: portability and semantics.
Okay, portability first.
Portability means the telemetry you generate using OpenTelemetry can be sent to pretty much any back-end system that supports it. You're not locked into one vendor's format or tools.
Ah, freedom. That tackles the lock-in problem.
Big time. And then semantic conventions. This means the data isn't just raw numbers or strings, it's self-describing.
What does that mean? Self-describing.
It means the data comes with rich metadata that explains what it is. Like, a metric won't just be HTTP server duration, it'll have units like milliseconds, maybe labels saying which route it was for, which HTTP method. It makes the data much easier to understand, visualize, and query automatically.
Got it. So the data carries its own context. That sounds incredibly useful.
It is one source called OpenTelemetry, a major evolutionary step, kind of bringing together the best ideas from the last couple of decades in this space.
So it builds on previous efforts.
Definitely. Things like open tracing and open census were precursors, and OpenTelemetry merges and expands on them. It aims to be that single, unified standard.
And how does this actually help the people involved, developers, ops teams?
For developers, having this consistent telemetry, this schema, is almost like built-in documentation. Traces, for example, show exactly how code flows, how libraries interact. It helps you understand usage, find common mistakes, even tune configurations better.
So the telemetry itself helps you understand the code.
Cool. Yeah. And for operators, it makes correlating signals much easier. You can connect application performance data, like a slow request trace, with infrastructure data, like CPU usage on a specific virtual machine or a Kubernetes pod event.
Ah, connecting the dots across layers.
Exactly. That isolated data point suddenly becomes much more meaningful when you see it in context. It helps pinpoint root causes way faster.
And for the organization as a whole, less tool juggling, maybe lower costs.
Potentially, yes. A more unified approach, less need to build everything custom, flexibility in choosing back-end tools. It empowers teams by giving them consistent access to different types of telemetry in a standard way.
Okay, so OpenTelemetry sounds like a big deal. How is it structured? Is it just one thing?
No, it's a collection of specifications, APIs, SDKs, and tools. There's a formal specification process using OTEP's OpenTelemetry enhancement proposals.
Like how internet standards are made?
Kind of, yeah. It keeps things consistent across different languages and allows the community to contribute and evolve the standard.
Smart. And what are the key pieces we should know about?
Okay, several key components. Context propagation is huge for tracing. It's how OpenTelemetry carries identifiers, like a trace ID, across different services, threads, async calls, so you can link everything that happened as part of one single request.
The thread that ties it all together.
Exactly. Then you have automatic instrumentation libraries. These are lifesavers. For many common frameworks and libraries, web frameworks, database clients, you can often just add the OpenTelemetry library and it automatically instruments things for you.
Oh, nice. Less manual work.
Much less. There's also the OpenTelemetry protocol, OTLP. That's the standard network protocol for sending telemetry data from your app or an agent to a collector or a backend. Vendor neutral.
The universal language for this data.
Pretty much. Then there's the concept of a resource in the SDK. That identifies what is sending the telemetry, like service.name checkout, instant.id, XYZ123, essential context.
Got it. Source identification. What about the trace data itself?
Traces are made of spans. A span represents a single unit of work, like handling an HTTP request or making a database call. Each span has a trace ID, linking it to the overall request, its own unique span ID, usually a parent span ID, showing who called it, a name, start end times, attributes, key value tags with details, events, time-stamped logs within the span, and a status like success or error.
So lots of detail in each span.
Yeah, they form that detailed picture.
Yeah.
And related to context propagation, there's trace context, which is the standard way to pass trace IDs around, and baggage, which lets you pass custom key value pairs along with the trace, maybe for specific business context.
Like adding your own notes to the trace.
Sort of, yeah, for specific debugging info you define.
What about metrics and logs?
OpenTelemetry has a metrics API too. Different instrument types like counters, things that only go up, down counters, things that go up and down like active connections, and histograms to see the distribution of values like request latencies.
Okay, standard metric types.
Yep. And configuring all this happens through a meter provider for metrics and a tracer provider for traces. They're like the central control points. Then you have span processors, which handle spans as they finish maybe bashing them up before sending, and exporters, which are the components that actually send the data out to your chosen backend, like Jaeger, Prometheus, or a commercial platform using OTLP usually.
So providers configure, processors handle, exporters send. Makes sense. I've also heard about the OpenTelemetry collector.
Ah, yes, the collector. It's a separate service, like a Swiss Army knife for telemetry. It can receive data in many formats, including OTLP, but also others like Jaeger's format. Process it.
Process it how?
Filtering, batching, adding extra attributes, maybe removing sensitive data, even sampling, and then it exports it to one or more backends. It's really flexible and can take load off your applications.
It's like a central hub for telemetry processing.
Exactly. And speaking of sampling, that's another key concept. Since tracing everything can be overwhelming and expensive, OpenTelemetry supports different sampling strategies to intelligently decide which traces to keep and which to drop.
Okay, that's a lot of pieces, but they seem to fit together logically. But it all hinges on getting good data into the system, right? Instrumentation.
Absolutely critical. As one source put it, good instrumentation drives observability. You can have the best tools, but if your code isn't emitting the right signals, you won't get the insights.
So developers need to think about this.
Ideally, yes. There's this feedback loop. You ship code, you observe its behavior using telemetry, you learn, you improve the code and the instrumentation. Some places even push for putting software engineers directly on call for the code they write.
Ah, the you build it, you run it idea.
Exactly. Nothing motivates better instrumentation than knowing you might be woken up at 3 a.m. because of it. You'll want the data to fix it fast.
Makes perfect sense.
Okay.
Let's shift focus slightly. How does all this apply specifically to microservices? That architecture seems tailor-made for observability challenges.
Oh, definitely. Microservices are inherently distributed, many small, independent services talking to each other. As the microservices up and running source points out, this immediately creates challenges.
Like what?
Well, data is isolated within each service, so understanding a request that flows through 5 different services, you absolutely need distributed tracing, using that context propagation we talked about, to see the whole picture.
Otherwise, you're just seeing tiny, disconnected pieces of the journey.
Precisely. You can't just look inside one service's logs anymore. You need that end-to-end view that tracing provides. Observability helps you map out those complex interactions and dependencies.
And I guess identifying where a bottleneck is becomes crucial when multiple services are involved.
Absolutely. Is it service A, service B, the network between them, some downstream dependency? Tracing and correlated metrics help you pinpoint that much faster. Root cause analysis gets a massive boost.
Makes sense. The sources also mention infrastructure as code, IAC being important here, like Terraform.
Yeah, that's key. Because microservices often run on dynamic infrastructure, like Kubernetes. Having your infrastructure defined as code, IAC, provides consistency and auditability.
How does that help observability?
If your infrastructure is consistent and predictable, it's easier to interpret the telemetry coming from it. You know what you're observing. If environments are manually configured and drift apart, correlating telemetry becomes much harder. IAC provides that solid, reliable foundation.
Got it. Consistent infra makes for more reliable signals. And these microservices are often in containers, right? Docker, Kubernetes.
Very often, yes. So your observability tools need to understand containers and orchestration. They need to automatically discover services, handle those ephemeral instances, and correlate data from the application with data from Kubernetes itself.
So the tools need to be cloud native aware.
Exactly. And observability can even help you evolve your microservices. By looking at the traces and dependencies, you might realize, these two services are always talking to each other, maybe they should be merged. Or this service is doing too much, let's split it.
Oh, interesting. So the data guides the architecture.
It can, yeah. The sources also mention patterns like event sourcing and CQRS, which are common in microservices. Observability is vital there too, for tracking event flows and understanding the separate command and query paths.
And with microservices, you tend to release updates more often, right?
Yeah, independent deployments are a big advantage, but you absolutely need observability to understand the impact of each release. Did latency increase? Did error rates go up? That fast feedback loop is essential for safe, continuous delivery.
Okay, so observability is pretty much non-negotiable for doing microservices well.
I'd say so, yes. It's fundamental to managing that inherent complexity.
Now, we also looked at sources specifically about .NET performance. How does understanding .NET internals connect back to observability?
It's super relevant because the behavior of the .NET runtime itself directly impacts the telemetry you collect and what it means. The .NET Performance book covers a lot of ground here.
Like what kind of things?
Well, basic stuff first, like using .NET Performance counters. These give you built-in metrics for things like CPU usage, memory allocation rates, and critically garbage collection activity.
The GC, yeah. Always a big topic in .NET.
Absolutely. So those counters provide a baseline, like the vital signs for your .NET app. They often feed directly into your observability metrics.
And you mentioned ETW events earlier. Event tracing for Windows.
Yes, ETW gives you much deeper, finer-grained insights into the CLR, the Common Language Runtime. You can see specific events like when a GC starts and ends, when code gets JIT compiled, when exceptions are thrown.
So that's for really deep dives.
Exactly. If your high-level metrics show a problem, ETW tracing, or similar mechanisms on other platforms, can help you pinpoint the exact cause within the runtime itself. Maybe you see tons of general GCs pointing to excessive short-lived object allocation.
Right, the garbage collector. Understanding that seems key.
Totally. The source goes into detail about GC generations. Gen 0, 1, 2, the large object heap, LOH, different GC modes, workstation versus server, concurrent background. Why does it matter for observability? Because GC pauses can directly impact request latency.
Ah, so a spike in latency might actually be the GC running.
It absolutely could be. Observability tools can help you visualize GC pauses alongside request traces, so you can see that correlation. And if you're trying to optimize, like using object pooling to reduce allocations, your telemetry should show less GC activity. It validates your efforts.
Okay, so you use observability to see the impact of GC and your tuning efforts. What else from the .NET world matters?
Things like boxing and unboxing, converting value types to objects and back. The book notes this can add overhead. Observability might not show boxing events directly, but it could reveal symptoms like higher allocation rates or more GC pressure.
Indirect clues.
Yeah. Also, the just-in-time JIT compiler. How fast your code gets compiled to native code affects startup and runtime performance. Observability can track things like startup time or method execution time, which can reflect JIT behavior.
And asynchronous programming. Tasks async await.
Crucial in modern .NET for responsiveness. Observability, especially tracing, helps you follow the flow of async operations, see where time is spent waiting, identify potential thread pool starvation issues. It helps ensure you're actually getting the benefits of async.
Makes sense. You need to see if your async code is actually running efficiently.
Right. Even things like pinvoke calling native code can have performance cliffs. Tracing can show if calls into native libraries are unexpectedly slow, and even the choice of .NET collections matters.
How so?
Using a list T versus an old array list, or using concurrent collections correctly in multi-threaded code, these choices impact performance. Observability can help spot if inefficient collection usage is causing bottlenecks, maybe through high CPU or latency in specific code paths.
And finally, network stuff.
Yeah, network calls, serialization, deserialization, it all adds latency. Distributed tracing is perfect for seeing how much time is spent waiting for network I/O or processing data coming over the wire. It's all part of that end-to-end picture.
Wow, okay. So understanding the platform, like .NET, is really important context for interpreting the observability data you get from it.
Definitely. The raw data is one thing. Knowing what it means in the context of your runtime and application is key.
This has been super comprehensive. So wrapping up, what are the practical takeaways? How should organizations approach this?
Well, the first thing is recognizing it's not just a technical change, it's cultural too. Getting developers and operators thinking in terms of observability using the data, that takes effort.
So start with the people and the mindset.
Yeah, and don't try to boil the ocean. One source strongly advises starting small. Find the biggest pain points your teams have right now. Is it slow troubleshooting, frequent outages? Focus on using observability to tackle that first.
Show value quickly.
Exactly. Demonstrate the wins, get buy-in, and actively participate in the community. There's so much knowledge sharing happening around OpenTelemetry and observability practices.
And the build versus buy question for tooling.
The consensus seems to be, unless observability tooling is your core business, leveraging existing commercial or open source solutions usually offers a much higher ROI.
Why reinvent the wheel?
Precisely. Building and maintaining a scalable, reliable observability platform is a massive undertaking. Let the specialists handle that and focus your engineering on your own products. The space is evolving so fast, too, it's hard for an internal platform to keep up.
Okay, so key takeaways. Complexity is the new normal. Traditional monitoring isn't enough. Observability lets you ask new questions.
Yep. And tools like OpenTelemetry are crucial enablers, providing that standard portable way to get the telemetry you need.
And understanding your whole system distributed flows, platform internals like .NET GC is vital for making sense of it all.
Absolutely. It's about moving from guessing to knowing, using data to drive decisions and resolve issues faster.
This has been incredibly insightful, really helps clarify why this is such a hot topic. Thanks for breaking it all down.
My pleasure. It's a fascinating and really important area.
So, to leave you, our listener, with something to think about, with this growing power to observe almost anything inside your systems, what are the most unexpected things you might discover about how they really behave? And how could that knowledge fundamentally change how you approach building and running software?
Ooh, that's a good one. What hidden assumptions might be revealed?
Exactly. Something to ponder. We definitely encourage you to dig into the sources we discussed if you want to go even deeper. There's a lot more there.
For sure. Keep diving.